Tusha, welcome to this section. Do you want to try your microphone and your screen sharing?
Hello. Yeah. Can you hear me?
Yes, I can hear you. Would you like to try your screen sharing?
Yes. Yeah. It's showing other participant already shared the screen. So maybe you are sharing screen now. So that's why
Yeah,
you have to unshare first.
yeah.
Is it visible?
Yes,
I shared my screen.
It is working.
Okay. Okay. Fine.
Okay. We are about. Okay, perfect.
Thank you. Yeah.
So we are about to start. So just a few announcements. So I suppose everybody have checked the schedule. I will
Hello.
show it. Yes.
Yeah. Actually, I had one more talk. I have one more talk at 10:20. Sorry. So I'll join just after a few minutes. Is that okay?
Okay. Okay.
All right.
Sure.
Okay. Thank you.
Okay. 10 o'clock. In which time zone?
Sorry, it is in IST. I told it should be like after I have third talk in that panel, in this panel.
Okay.
Right. So I'll join after a few minutes.
So your talk. Let me see. Your talk will be 7:35 in Central European time.
Right.
You are able to come, right?
Yes. Sure.
Okay. Okay. Great. Okay, just a few official announcements. So I will show the schedule again, and so that people know which talks we are going to have in this section. By joining this section, participants, including all of you, agree that the meeting will be recorded. Okay. And I've checked that the recording is active now. And also during the talk, I will recommend people who are not speaking to mute so that we don't have so many noise. And this session will be automatically switched off by the organizer 15 minutes after the section ends. That will be in 3 hours and 15 minutes. So please be on time. But I think we are now to start. So let me share my screen again. So this section is the second slot of about pulsars. Okay, so it's more. It was supposed to be more focusing on high energies, but anyway, we will have a lot of exciting results from theoretical and observation point of views about pulsars. We will have 6 talks, and in between we will have 10 minutes coffee breaks so that you can go to toilet or for a break or drink coffee. So if there's no problem, then I will stop sharing and ask the first speaker, Professor Ho Zhao, who will be talking about extended TV gamma ray halos around pulsar, Gaminga pulsar. So please. How are you speaking now? I can't hear you.
Okay. Yeah, sorry. I did the screen sharing, but forgot
You can
to
just start
unmute.
over again.
Okay. Yeah, I assume you can see my slide now. Okay, I will start. Yeah, thank you. Thank you for the invitation. It's my honor to talk about the TV halos on behalf of the Hawk collaboration. So I think our story starts from the Gaminga pulsar. As you can see, the background image is a TV gamma image in the Gaminga region, which shows the very extended gamma emissions around this Gaminga pulsar and another monogen pulsar. So the size is actually much larger than the apparent size of the moon, which shows this this huge gamma resource spectral morphology. Okay, so sorry. Okay, so why Gaminga is an interesting pulsar? So first, it's the first example of the TV halo class. In 2017, Hawk published a paper reviewed this very extended gamma emission around Gaminga and represented a new source class TV halo. But Hawk is not the first experiment which see this this source. Actually, back to I mean, let's just go backward in time. Back to 2009, Milagro experiment, which is the predecessor of Hawk, published its gamma catalog, and Gaminga is one of them. And so Gaminga is interesting not only because it's the first TV pulsar halo, but also the pulsar itself is very interesting. So back to 1991, Rosette observed the pulsar emission in soft X-rays. So we know Gaminga is a pulsar, but we don't see any radio pulsation from this pulsar. So it's one of the first pulsars, so-called radio quiet pulsar class. But I mean, that was the 90s, but actually there are 2 decades before that, people know there's a gamma source around Gaminga, but don't really know what's the nature of it, because they don't see a position for a long time. So back to 1972, the small astronomy satellite 2 discovered this Gaminga source of Gaminga. So, and I mean, it's given name Gaminga. One reason is a combination of the Gemini gamma source, but also it's in some European dialect, I forgot the name, but it means Gaminga means it's not there. So which shows how confusing how confused the people were during the time. And I also noticed like the people in Europe and in Asia like to call it Gaminga, and from the US people are more likely to call it Gaminga. So it feels to me that Gaminga maybe might make more sense because coming from the word Gemini. But anyway, so Gaminga is interesting. Also, I mean, recently also because the connection to the local cosmic positron exercise. So the we know there's the positron fraction is larger than what we expect from the secondary cosmic ray model, galaxy. And this was first discovered by the Pamela satellite and later confirmed by AMS. And so about the origin of this positron exercise, people have a lot of different theories. One of the most exciting theory or hypothesis is the signal from dark matter. I mean, when dark matter particles annihilate or decay, they can make positrons and observed by us. I mean, contribute to our local cosmic ray spectrum. And also another possibility people proposed is there are might be nearby astrophysical sources like pulsar since we know pulsars can accelerate positron and electrons, and if a pulsar is close enough and energetic enough, they can the positrons can make to the Earth and contribute to our local mirrored cosmic ray spectrum. So we have to use our observations to distinguish these two scenarios. Okay, so
how can you hear me? Seems the internet. How we dropped you. I'm sorry. The speakers. Okay. How? Hey, can you hear me?
Yeah, I can hear you. Can you hear me now?
For 2 minutes, we could not hear your voice.
Hear me now?
Yes, but your internet connection seems not very stable.
So should I go ahead? So I'm not switching, switch to my. Yeah, is it better now since I've switched to my phone, to my hotspot?
It is better now.
Okay. Okay. From here.
Yes. Could you show your slides again?
We have.
I'm sorry. We seems to lose our speaker. So what if since we are, so I suggest maybe let's wait for 1 more minute. Oh, okay.
Okay. Sorry. I'm back.
Yes. Yeah. We have lost you. So can you make sure that you have the best internet connection at your place?
Uh,
Are you here, How? Okay, it seems that the speaker's internet connection is not stable. So let's switch our schedule. So Akansha, are you ready?
Sure, I'm ready.
I suggest that maybe you and Tasha, that you please start your talk, and then let's wait for how after your talk.
Okay.
Yeah. I'm sorry. Yeah. Thank you.
No problem. So you're seeing this okay?
Yes.
Okay.
Please go ahead.
Okay. So hello. First of all, thank you to the organizers of this event for giving me this opportunity to present some of my work. So my name's Akanksha. I am a master's student at Queen's University in Ontario, Canada. So today I'll be discussing some of my earlier work from the University of Toronto, where I was very lucky actually to be part of some very interesting observations from the Crab Pulsar. And these observations have allowed us to do some really cool, new, exciting science, which I hope to share that you'll find this interesting as well. So currently this result is in the process of being published, but if you would like to know more, you can see our draft on archive, and I've listed the archive number here. So just before I dive into the details, I'd like to give a quick overview of why this result is actually interesting. So we know that currently, you might be aware, the actual physical mechanism behind the radio emission from pulsars is not well understood. There are a lot of theoretical models, but there aren't very many observational constraints that allows us to narrow these models down. So what we're doing in our work is we're proposing the first ever direct measurement of the Lorentz factor of the source that is emitting these radio pulses. And so we measure a gamma factor on the order of 10 to the 4, which is implying, sorry, I'm just going to check the chat. Oh, okay. Which is implying that the motion is highly relativistic. And we also find that the plasma is relatively cold. And so this is interesting because not only has this never been done before, this also allows us to constrain theoretical predictions, which have a wide range in gamma. Some predict a gamma on the order of 1, and other theoretical models can go up to about 10 to the 7. So to begin, our observations are of the Crab Pulsar. So the Crab Pulsar is very famous and widely studied. It is the remnant of the supernova that went off in the year 1054, which was recorded in a lot of historical texts. So this is a very young pulsar and also rotates very fast. And it's also one of a handful of pulsars that are known to emit giant pulses. So as the name suggests, giant pulses are much brighter than regular pulses. And if we compare their duration and their luminosity, we see that giant pulses are both much brighter and much shorter than regular pulses. Their brightness temperatures can even go up to about 10 to the 37, making them some of the brightest sources of radio emission in our sky, just shy of fast radio bursts or FRBs. Actually, there are a lot of similarities between giant pulses and FRBs. Both are coherent emission and have a high polarization fraction. And so for this reason, many people have wondered whether FRBs are actually just giant pulses from very young, rapidly rotating pulsars. And in fact, this gap between the two might even be filled by FRBs that are closer to us if we are able to observe more. And so not only would understanding the radio emission of giant pulses help us to understand pulsars, it might also help us to understand FRBs as well. So all of the observations that I will be showing were taken from the Algonquin Radio Observatory, which is a single 46-meter dish in Ontario, Canada. And these observations were taken from 2015 and 2018 in the 400 to 800 megahertz band, which is the same as the chime band. The observations were taken with the intention of doing some interferometry, some VLBI, with another telescope, which is the Dominion Radio Astrophysical Observatory, or DRAO, in British Columbia. So this is about a baseline of 3,000 kilometers. For our analysis, we actually don't do interferometry. We're just working with all of the pulsars from ARO. But because there is some overlap in data, we do sometimes look at the DRAO data just for confirmation, as you'll see shortly. So in this 400 to 800 megahertz bandwidth, one of the effects that comes into play for this relatively low frequency observations is something called interstellar scattering. So interstellar scattering is a propagation effect. So once we have our pulsar emit spatially coherent radiation, it's going to come across variations in electron density within the interstellar medium. And so these variations are going to have different refractive indexes, which will cause our waves to have different phase shifts or different time delays as observed on Earth. And so what we can do is we can model these phase shifts at scattering screen, which is located midway between us and the pulsar. And so the difference in path length can be modeled as some angle that is being bent by this screen into our line of sight. And this angle, change in viewing angle, is frequency dependent. So so the amount of scattering that we see depends on the observing frequency. So lower frequencies are going to have a much more pronounced scattering effect, as well as bend in viewing angle, whereas higher frequency observations will not have that much scattering. So the difference in path length will also result in an observable time delay, or scattering time length. So specifically for the Crab Nebula, we place the scattering screen along the Crab Nebula. That's where most of the scattering happens. And so the scattering time is goes about frequency to the fourth. And we can see this in our giant pulse observations. So here I have an observation taken from ARO, which is going from 400 to 800 megahertz. And what you see is that for the lower frequencies, you're getting a broadening in the pulse width. And so this is a result of scattering, and this is our scattering timescale. And even in the averaged time profile, you can see that there is a broadening of the pulse, and this is known as the scattering tail. So comparing this to observations at high frequencies, as I mentioned, the scattering effect is frequency dependent. So at high frequencies, we don't actually expect to see the scattering effect. So previous studies by Hankins et al. Have done an extensive work to characterize giant pulses at high frequencies. And what they found is that there's two types of pulsar emission at high frequencies. So the first is where you see a lot of substructure within the duration of the pulse. So remember, this is now the intrinsic duration of the pulse. There's no scattering here. So what you see is that there's several mini pulses, or what they're calling nanoshots, of nanosecond duration within the microsecond duration of the pulse. And the second type of emission that they see is looks quite different. And this is known as spectral bend, what they're calling spectral band emission, where you're seeing zebra-like stripes in frequency, where you have a brighter and darker banded sort of pattern. And so what they propose is that these two types of emissions are actually occurring from different emission physics. And so what we have done is we have also tried to categorize our gallery of pulses just based on eye by eye features that we can pick out. And so we've placed our pulses into different categories. So I looked at about 148 pulses by eye. And I'm just showing some of the brightest few from 2015 and 2018. So the first category of pulses are just the typical ones that we usually see. So this is the pulses that we're going to call regular pulses. So once again, you see scattering at lower frequencies at around 400 megahertz. and our usual pulse shape, and we see emission throughout the entire frequency band. And we have an exponential scattering decay, scattering tail, which has exponential decay. So here are the pulses that match this regular description. In our second category, we're calling these double peak or multi-peak pulses. Here you can clearly see that there looks like there is more than one pulse. I should mention that this isn't a new observation. This has been seen before. It just seems to happen randomly, and it's not that interesting for this talk, but just that's one of the categories. Another category that we placed pulses into was if there wasn't emission throughout the entire band, but it was just in a narrow band of emission. We're calling these partial pulses. Again, this is not the interesting or the point of the talk, but just to show you the variety in the types of features that we're seeing. A fourth category is the spectral banded pulses. So this is similar to what was observed at high frequencies by Hankins. So we see this again at low frequencies. So again, we're seeing zebra stripe-like pattern of light and dark of these bands. And within our replacing these three pulses into that group. A subcategory of these banded pulses is some of the bands appear to shift within the scattering tail. So we're calling these drifting bands, drifting pulses, where it looks like the band is not constant throughout the tail, is most obvious here, but seems to drift either upward or downward. So just to zoom in so you can see what I'm talking about, here we have a regular banded pulse. And then just so your eye is able to trace the pattern that I'm talking about. So these are the drifting pulses or the shifts in the scattering tail of the spectral bands that we're seeing. This is really the focus of my talk. And so this is the new observation and the interesting observation that we want to understand why these bands are drifting in the scattering tail. And so that's really the question that I'm going to try and answer during this talk. So the first time we saw this, of course, we wanted to know what was going on. And immediately you might also be thinking, well, could this be an instrumentation effect, this drifting of the spectral bands? So we do have some overlapping data with our other telescope, DRAO. So unfortunately, we didn't have any of the drifting bands that were overlapping at DRAO, but we did check some of our banding pulses, and we see that the spectral banding pattern is also visible at DRAO. So we can rule out the banding being an instrumentation effect. We also checked the data of the drifting pulses at ARO just to see if there were any sort of obvious deficiencies in the data, or if we could pick out anything weird that was happening, and we didn't find anything. So we've ruled out instrumentation effects as a possible source. We also wondered whether it could be the scattering environment that is causing these types of patterns. So for example, like echoes that have been observed in the Crab Pulsar, these echoes last for timescales of days and weeks. And so we were wondering whether these spectral patterns, the bands and the drifting lasts for more than just one pulse, whether these patterns persist. So what we decided to do was we checked the pulses around the ones that showed the banding. So in the second column, I'm showing the next brightest pulse within the 10-second neighborhood of the first column. So you're seeing the next brightest pulse, and all we're really trying to see is if the banding pattern persists. And so we find for all of these, the next brightest pulse looks regular and doesn't look like the banding pattern persists. Similarly, we took an average of the 30-second neighborhood around this pulse. So now we are aligning all of the pulses and just summing and taking an average, just to see if any of the more fainter pulses perhaps have this banding pattern. And again, we find that the average also doesn't seem to persist the same pattern. So this tells us that if it was something to do with the scattering environment, we don't actually expect the scattering environment to change on the time scale of seconds. So this banding is changing on the time scale of seconds, whereas something like echoes change on the time scale of days and weeks. And so we don't think that it is the scattering environment. Another possibility was that perhaps this banding pattern is due to scintillation. But for there to be interstellar scintillation for the Crab Pulsar, first of all, the Crab Pulsar is not a point source to the scattering screen, and so we don't expect interstellar scintillation. There could also be interplanetary scintillation, but if you work out the decorrelation bandwidth, actually it's larger than our 400 megahertz band, and so we don't expect to see interplanetary scintillation as well. And so we can rule out instrumentation, scattering, and scintillation as possible reasons for seeing the bands and also the drifting. So if it's not these effects, the question is, what could it be? So for now, we are going to assume that the spectral bending is actually an intrinsic feature of the pulsar emission. We'll revisit this assumption later on, but for now, that's the assumption that we'll go with, and we'll focus instead on what is causing the observed drifting. So one clue just from the observations alone is that we see that the observed drifts are happening in the scattering tail. So if you remember our discussion about the scattering, this is giving us a hint that perhaps the drift is related to our viewing angle from the scattering screen. So that is one hint that we're getting from the observation. And so let's see what our proposed model is. So this is the picture that we are proposing. So what we're proposing is that the source of the emission, let's say a blob of plasma that is being emitted, is going to be traveling at some speed from our line of sight at an angle. And so if we assume that this blob is traveling highly relativistically, then the frequency that we receive is going to depend on this angle as by a Doppler factor, as you know. And since we're going to have the effect of relativistic beaming, the angle from our line of sight can't be that big. And so we can apply a small angle approximation, and we can also approximate gamma to be much larger than 1. And so that gives us a simplified value for the Doppler factor. And now we can add in the effect of scattering from the Crab Nebula. So we're going to have our viewing angle change by some delta. And so we can find what the change in our received frequency would be if we change our angle by some delta. Now we're going to consider the more statistically likely case that we are at the edge of the beam. So exactly as I've drawn here. So if we're at the edge of the beam, we expect that our change in frequency is going to be proportional to our viewing angle delta. So what we can do is we can also use our known geometry of the screen, the scattering screen for the Crab Nebula, to estimate what this change in viewing angle will be. So what we can do is we can use previous works which have estimated the scattering screen to be a distance of about 1 parsec from the pulsar. And then we can estimate our scattering time as just from the observation alone. So we see that the scattering time is about 0.5 milliseconds. And then this gives us about, a scattering angle of change in viewing angle of about 0.6 arc seconds. And we can also estimate the change in frequency just from our observation, and we see it's about 4%. And so that gives us a measurement of gamma to be on the order of 10 to the 4. So the question is now, does this very simple model actually match the data? So following our model, we see that the change in the received frequency is proportional to the scattering time as going as square root. And just by eye, it actually does look like it follows a square root dependence. But we can do better than this. So what we can do is we can actually take the initial intensity of the data, and we can evolve this for different times and different frequencies. So we can shift this by frequency. We can apply our Doppler boosting, and then we can also exponentially decay this with time. And so we can just have one free parameter that we adjust, and we adjust this free parameter by I, and we've set it to a 0.028 here. And we find that just by I, it does look like the model actually is able to recreate the data quite well. And here we're showing the residual. So just that simple model, and we are able to recreate our data. We can also do this for different time slices and frequency slices of the pulse. So here we were showing a 2D image, but we can also slice this for time and frequency. So taking different time slices, taking different frequency slices, I can evolve the first time slice. And so here the model is shown in black and the data is shown in blue. So first, the model is just a fit of the data, and then later we can evolve the black model using our model. And we find that the peaks, which are the frequency bands, again, actually do seem to follow the data quite well. Another thing we want to check for is this Doppler boosting factor. So looking at the different frequency slices, we want to see whether the intensity of the model and the drifting pulse are actually boosted higher than what would be for an average pulse. So here we're comparing with the brightest neighborhood, which is shown in the dotted gray line, as well as an average of 30 seconds around the pulse, just to see if the drifting pulse, the Doppler boosted pulse, is actually boosted or not in luminosity. So it's a little hard to see, and it's not quite convincing, but at times it does appear that the drifting pulse and the model are slightly above the average, for example, here. But this is still quite inconclusive, and I don't think we can say for sure that we've measured the Doppler boosting factor. Okay, so another thing we can do is we can also estimate what the range in the Lorentz factor should be, what the spread should be. So if we measure what the full width half max of one of these frequency bands is, we see if we divide that by the central frequency, we see that there's about that this is about 4%, and so our change in gamma should also be less than or about 4%. And so this is implying that the plasma is relatively cold, which is also a result of this model. So earlier we assumed that the spectral bending pattern was coming as an intrinsic emission of the pulsar, but we can also relax this assumption. So for example, we can consider that the spectral bending pattern is actually an interference pattern between the multiple nanoshots. So if you recall, nanoshots were the substructure that I showed you in high frequency. So if we have some trigger that is giving off the emission and gives off several different nanoshots, then these can interfere with each other if they're separated by about, in path length, by about half a wavelength. And then using our observational wavelength, we can estimate that this distance would be about 100 kilometers. But for them to be causally related, this would have to be actually moving superluminally with a factor of 10 to the 4. So once again, we arrive at the same conclusion, whether or not we use an intrinsic emission of the spectral banding, or if we say that the banding is from perhaps interference of nanoshots, we arrive at the same conclusion that whatever the source is emitting must be moving relativistically.
Akansha, you still have 2 minutes.
Okay, thank you. Okay, so some of the implications of this model is that while we only observed upward drift was the one I showed you that was the most obvious by eye for that pulse, it also depends on the scattering geometry. So we know that the scattering geometry, again, moves around as a pulsar moves, the scattering geometry changes on the time scale of weeks. And so we expect, for example, if the geometry was slightly different, let's say we had a more symmetric geometry, that you would see a mix of both upward and downward drift. And perhaps this is what we're seeing in the other pulse that I showed earlier, pulse F, Like certain parts look like perhaps they are drifting downward, but other parts look like perhaps they're drifting upward, though it's not too obvious by eye. But a way to test this model is to look for either more upward or downward drifting pulses, since we predict that you should be able to see both. We also predicted that there's a small range in gamma, so the plasma is cold, and that the intensity should be boosted in the scattering tail by about 10%, and that the physical separation, going back to this, was about 20 light nanoseconds. So I mentioned earlier that giant pulses are similar to FRBs. And so could this highly relativistic motion have any implications for FRBs? And so FRBs have also been shown to show drifts, what is typically referred to as the downward march. There's always these three pulses, that substructure pulses that seem to march downward. However, since the FRBs always have a systematic downward drift, this is likely not the same as what we're seeing for our giant pulses. But there could be implications that FRBs are also have highly relativistic motion as the source of their emission. So going back to the Hankins high frequency observations. So there was one observation by the Hankins pulses where it does seem to have a slight upward drift. They also mentioned in their paper that why this is happening, and they only found one such pulse that does this. However, comparing this to our low frequency observation, I just want to be a little bit careful to point out the differences. At our lower frequency observation, the drift is happening in the scattering tail, which is the main reason that we have interpreted this as a change in viewing angle. Whereas at high frequencies, this is the intrinsic duration of the pulse, and the scattering is not obvious here, so this is not happening in the scattering tail. And so we propose that this drifting pulse at lower frequencies is actually from a different mechanism than the one that was observed at high frequencies. So some of our next steps is we want to look for more drifting pulses. So far, we only have the one that is obvious by eye and maybe another one. And of course, we want to do this for even lower frequency observations such as LOFAR, since the change in viewing angle will be much larger and the scattering tail will be much larger. So hopefully we'll be able to observe this effect more obviously. And if we're able to find either downward drifting or boosting in the scattering tail, then that will give us an indication that this model is correct or on the right track. We want to also be able to do a statistical analysis of the giant pulse characteristics. So how I showed the double peak and the partial pulses, perhaps there is some grouping or statistical properties there. And finally, observations of FRBs with large scattering, we could also try to tie that in to have a more cohesive picture. So to summarize, we saw this really cool observation of a giant pulse, low frequency giant pulse of the Crab Pulsar in 400 to 800 megahertz band. We interpreted this shift in the frequency band as a Doppler shift that is caused where our viewing angle is changing across the scattering screen. And so we're receiving a different frequency for the pulse that is arriving with a time delay. And this allowed us to measure a Doppler factor on the order of 10 to the 4, which allows us to constrain theoretical predictions that range from 1 to 10 to the 7. So thank you for listening. And I don't know if we are going to leave time for questions, but if there are any questions, I'll be happy to take them now, or you can send me an email. Thanks.
Yes, thank you. So I think we'll welcome one question from the audience, if there is any. So maybe I have one layman question. Do you see any evolution in the Crab giant pulses over the years?
Yeah, that's a good question. So for years, we see differences. Again, the scattering geometry is changing. There's also the dispersion measure, I think will also change on the scale of months. So just from the pulsar moving and slight variations like that. So one thing that we were kind of guessing, but we didn't actually quantify was, maybe I can go back all the way. Was that the 2018 scattering tail on average looked longer than the 2015. Just by eye, we were kind of thinking that that was perhaps true. So I think even the scattering timescales on the timescale of years can possibly change.
Okay, thank you.
Thank you.
So if there's no more question, let's thank the speakers again. And we'll move on to the next talk by Tusha. So who will be talking about spin-down evolution of magnetars, a novel approach to estimate their ages. Are you ready, Tusha?
Yes.
Yeah.
Can you share my screen, right? Am I audible?
Perfect. Please start.
Okay, thank you. Good morning, everyone, and thank you very much for giving me this opportunity. So I'll talk about spin-down evolution of magnetar, a novel approach to estimate their ages. So we all know that anomalous X-ray pulsar and soft gamma ray repeaters are the two kinds of observations which prove that magnetar existence observationally. So you can see that SGR and XP both are like share some common interesting properties. So one is the rotational period in the range of 2 to 12 seconds and the spin down rate in this zone. So if we see the period derivative versus the spin period, so you can see that all the radio pulsar is sitting here in this zone, but most of the magnetar like SGR or XP sitting in this zone, like clustering in a small period zone like 2 to 12 seconds, and the period derivative is in this like very high. That means the magnetic field measurement also will be very high for these sources. So one can notice that electron quantum magnetic field limit is in this line, dot dash line. So all that SGR XP, the magnetic field coming from that magnetic dipole approximation measurement, like one orthogonal vacuum dipole model. So if we write down this and if we take that like 10 solar mass, 1.4 solar mass neutron star and 10 kilometer radius, then the magnetic field can be calculated from the spin period and the period derivative. So you can see all that SGR XP lies very high magnetic field, and to explain their persistent X-ray luminosity, the spin down energy cannot explain this large luminosity. So another interesting mechanism is that magnetic field decay scenario is very important in these cases. So the important thing is that there is some challenge happening in this SGR and XP scenario after the discovery of these sources in early 2010. So this is known as SGR 0418 and plus 5729. This peculiar source is showing the period is clustering well in this 2 to 10 second zone, but the period derivative is lie far below. So if we calculate from the characteristics magnetic field from the timing properties, that means spin down properties, it come down 7 10 to the 12 Gauss, which is far below the electron quantum field limit. So to the other properties of that SGR XP, it shows like X-ray time luminosity is also very high, and also it show like burst like activity. So to explain the large luminosity, magnetic field is very low here. So there is no energy budget as like rotational energy as well as magnetic field also very low. But at the same time, after this discovery, there is some proton cyclotron resonance scattering features from that X-ray spectrum. It shows that magnetic field, surface magnetic field, come down to the 10 to the 14 Gauss. So you can see there is some discontinuity in this almost 1 order larger. So to explain this discrepancy from the timing properties and from the spectral properties for this kind of sources, so there are some discrepancies there. So in this talk, I will my first objective is the discrepancy measurement in the surface magnetic field from the timing and spectral analysis. The second important challenge is that not only the magnetic field strength, since the evolutionary stage of magnetar, like they are very young, and isolated neutron star, and also their age is varying from 10 to the 3 to 10 to the 4 year, it is very difficult to explain these sources, how old these sources are, apart from magnetic field strength. So second important challenge is the age measurement, or which type of supernova remnant is associated with this kind of magnetar. So as we all know that all radio pulsar or magnetar, so if we know their supernova remnant association, so we can explain their age and the magnetar birth stage, everything we can know. But there is some problem compared to radio pulsar and magnetar. So radio pulsar very easily can be distinguished, like this supernova remnant is associated with this radio pulsar from the judgment of these three particular agreement. One is their characteristic spin down edge. So as like dipole magnetic braking mechanism giving that characteristic magnetic field, in the same way we can get from the spin down parameter what should be the characteristic edge. Also, we know the transverse velocity. So if we trace back that radio pulsar to their supernova remnant associated birth stage, so from there we can agree that this radio pulsar is associated with that particular supernova remnant. Also, from the positional coincidence in the sky, we can also verify this association is confirmed or not. But the problem in magnetar, all these three agreement is failed for magnetar cases, because magnetar case this characteristic spin down edge does not follow, because this edge measurement is basically come down when magnetic field is constant, and also like vacuum dipole approximation model. But as we know that in pulsar, that is actually plasma field magnetosphere is there, and for magnetar one other fundamental properties is the magnetic field decay mechanism. So that is giving that energy budget for these sources, and it is already verified that characteristic age for some well-known sources where the supernova remnant association is known and it is observed last 30 years. So it is confirmed that characteristic age like 230 kiloyear for this AXP, where that actual age of that supernova remnant is that 14,000 year. So you can see there are large discrepancy in this actual age and the characteristic age. Also some other younger source like only 1,300 year, and their characteristic is basically showing 4.6 kilo year. So you can see all the sources, even for younger or older one, there are large discrepancy in that age measurement. So this point is not valid for magnetar. Second, also there is no fruitful mechanism of, or the range of transfer velocity is not found for magnetar. What is happening? So we cannot trace back that magnetar to particular supernova remnant association zone. So we have to rely only on the positional coincidence to associate one magnetar to the supernova remnant. So in this talk, I will talk about that actual age measurement of magnetar independently, not from that spin down parameter only. So to go along that magnetar spin down, so we take care about not only that vacuum dipole model, we'll take care of that plasma field oblique rotator model. So it's not like orthogonal, that means magnetic axis and that rotation axis is not perpendicular to each other. So we have to couple all that mechanism like magnetic field decay and spin down, and that alignment of that oblique angle is happening. So this is nothing but that spin down energy is basically taking care about the torque associated with gravitational wave, and this is electromagnetic wave. So first term gravitational wave, because the high magnetic field, it will deform the star, and at the same time high magnetic field will give one dipole radiation term which is proportional to sin square chi, and other particle wind term, because in the magnetosphere that high particle acceleration will be there, and it will depend strongly on the depth information of that pulsar or magnetar. So the depth information will also change if the magnetic field strength will also change, and the V gap is the potential gap in that open field line zone. At the same time, this torque also also try to align that oblique angle between magnetic and rotation axis of that pulsar. We have to take care about the magnetic field decay mechanism self-consistently. So this is magnetic field decay mechanism is basically taking care, and recent development of numerical simulation is taking that magnetothermal evolution of magnetar. So where we can take care that magnetic field decay mechanism happening by ohmic decay, Hall diffusion, and ambipolar diffusion mechanism. So it's come down that crustal field decay is mainly controlled by Hall cascade, where the Hall timescale and ohmic timescale is basically coming from magnetothermal evolution one. So to solve this self-consistently, if we see that we from observation that current value of d omega dt we all know, and also omega, that means spin period and p dot, p and p dot both we know. but the unknown parameter is the magnetic field strength and that oblique angle. So what we do, so current time means t is equal to 0, and we back in time that integration of all that coupled differential equation. So currently we know omega naught and d omega dt at t is equal to 0, but we don't know this parameter chi naught and b naught. Now if we fix one chi naught, so from that previous equation where the unknown parameter only the b and chi, so if we supply chi, so for each given chi we'll get one b like magnetic field. Now if we run back in time, so it will stop the code. Evolution will stop at that birth site where chi tends to pi by 2. So this is one specific boundary condition, because the newborn magnetar experience an evolution where internal viscous dissipation of damping of precision basically drives that chi tends to pi by 2 shortly after the birth. So it happened within few minutes. So you can safely take this is the birth site condition when chi tends to pi by 2. So that means for a given chi naught, we have a particular fixed value of Tz or that age of that magnetar. So we can specify, if we know that magnetar age, we can specify what should be the oblique angle of the magnetar. Or if we know that oblique angle, we can tell what should be the age. Now to study some this mechanism, first we tried some well-known AXP or SGR sources. So you can see 182259, as I mentioned previously, the supernova remnant association is well known, and also the age also known. So you can see if we vary that chi naught for a given chi naught, we can get a particular age of that magnetar and also specific value of magnetic field based on this bound. And in this bound, it's come down, you can see that bound of that age comes in very smaller region. So we don't have to rely on the supernova remnant association, because this is very challenging. That supernova remnant age measurement, it depends on a lot of other parameters like space velocity and distance of the source. So any error in this individual parameter will give the age measurement wrong. So in this way, where we record only spin period and spin period derivative, it can easily confirm the what should be the age bound based on this bound. Now, if we know that exact age of these sources, like from supernova remnant catalog, we can know that age of these sources like 1.3 kiloyear and one is 14 kiloyear. So I took here two different sources. One is older one and other is younger one. So you can see what should be the chi naught or what should be the oblique angle from this age measurement, where age will cut this particular angle. And at that point, we can get the specific value of magnetic field for these sources. So you can see that oblique angle for this 1841, that younger one is around 72 degree, whereas for oblique angle for 2259 AXP sources is around 40 degree. So that means it indicates that as the source older, the inclination of that oblique angle goes down close to the 0. So what should be the specific information of depth? So you can see that omega naught, that current value of omega naught, and is plotted against their depth rotational velocity. So you can see both the sources are well above their depth information. So you can see that other information, this 182259 is very closer to the depth. So the summary of this part is that the source, to give the pulsar-like activity, it has to be above their depth line. And as the source getting older, so it becomes that oblique angle becomes smaller and smaller, and the source goes towards their depth. Now, what happened for the other sources when the source lies already below their depth information? So these are the particular sources which is challenge the traditional picture of the magnetar, like the magnetic field come that very weak, which cannot explain their large luminosity. But here we see the sources already come below their depth for large obliquity angle, and the sources only lie above their depth line only for below 5.6 degree. For other sources like this also same things happening. So below 14.8 degree, these sources above their depth information. Since the sources give pulsar-like activity, so sources have to lie in this zone. So from here we can bound what should be the chi naught value for these particular sources, which shows that so-called low field magnetar, and these sources challenge the traditional picture of magnetar. Now, if we take care about this angle particularly, so you can see below this particular angle, the magnetic field is very high, like 10 to the 14 Gauss. But below this magnetic field lie below that quantum electromagnetic field line, when we calculated characteristic magnetic field, whereby taking chi is pi by 2 and 90 degree. So here you can see magnetic field is very low, but the actual situation the sources lies in this zone. So magnetic field is very high, and so the discrepancy is sorted out in this way. So it matches the timing properties and spectral properties very well. So it can resolve the solution. At the same time, we can calculate what should be the age of these sources. So age of the sources for specifying this chi-naught is coming down to 17 to 18 kiloyear. For the swift sources, it's come down to 18 to 20 kiloyear. So this way we can easily model what should be the age and magnetic field strength. Now, after assigning that particular chi-naught, you can see that evolution of that any time evolution. So you can see from that particular chi-naught specified, if we back in time, so after that age, it reached that 92. So this is the birth stage of that magnetar. And you can see the magnetic field evolution also happening. So here it is around 3 factor 10 to the 14 Gauss. So during birth, the dipole field almost order of 10 to the 15 Gauss. So in the p dot diagram, you can see the spin down evolution happening for all kind of sources. So as we take here two very low field sources and two sources which are known. Known means it follow the magnetar traditional picture, and two sources which does not follow the traditional picture of magnetar is basically they did not take previously. So last 10 years this problem was there because they did not take care self-consciously the evolution of oblique angle. So you can see that initially the p dot is slows down, and after come down because of the magnetic field decay is take care by the Hall cascade. So it comes down to the asymptotic zone or p, where p varies in the 2 to 10 second. After this asymptotic zone, that evolution is chi is very important from younger source to older source. So as it getting older and older, so p dot become lower and lower. So it can easily explain that chi dot becomes smaller and it goes towards their death, and it can easily explain the large luminosity. So the so-called low field magnetar are not actually low field magnetar. They are self-consistently chi naught is not taken care. So they are actually normal magnetar. So here we solve self-consistently the spin down evolution of magnetar by considering a plasma field oblique rotator model with state-of-the-art magnetic field decay mechanism whereby ohmic and Hall cascade is taken care. Also, the angular momentum extraction is happening because the rotational period increases because of the gravitational wave radiation, magnetic dipole radiation, and particle wind. So this talk also changed the obliquity angle, where last 10 years this problem is not taken care seriously, the change of obliquity angle based on this torque mechanism. And we unify all kind of SGR-EXP irrespective of their high as well as low characteristics magnetic field. The characteristic magnetic field measure only based on the vacuum dipole model mechanism, which is not viable for older magnetar because this is plasma field and these sources goes towards the death and their oblique angle becomes towards 0 degree. And also provide a novel approach to estimate the true age of the magnetar irrespective of their other parameter like supernova remnant we know or don't know. So it can indirectly correlate which supernova remnant is correlated with that other magnetar. And at the same time, it can also tell the age of that supernova remnant. So in this way, it can in future, it can say that magnetar birth sex mechanism. So for further technical things, interested one can follow this article. And thank you.
Thank you, Tosha. So we have some time for a few questions. So I think a natural question would be how your estimate of magnetar ages compare with other methods that has been proposed.
Compare with other methods. Can you repeat that?
So I'm not sure what are the other methods to estimate
Magnetic field, right?
Ages, yeah.
Right. So yeah. So first interesting thing is that as I mentioned, so the only way to measure directly the surface magnetic field of neutron star or any pulsar is that cyclotron resonance scattering features. where that energetic electron and because the background magnetic field is there, so scattering will happen, and depending on the magnetic field strength, so it will, like, resonance will happen at that particular cyclotron energy. So if we see that absorption line in the X-ray spectra and it is well fitted by that proton or electron cyclotron line, so it can easily tell what should be the magnetic field strength at the surface of the neutron star. So that is the only direct method to measure the magnetic field. Now, for magnetar, we hardly see the cyclotron line because observationally that also very challenging, because that absorption features, these are bursting activities is there. So we cannot correlate the which should be the absorption line. It can be well fitted with proton or electron cyclotron line. So that also very challenging. But if we get one cyclotron line, that can give lot of information like magnetic field exactly at the surface and what is the energy and broadening. So what are the constituent particle to make that absorption features in the spectra. So all that information we can get from the cyclotron resonance features, and that is very interesting. Other, the spin down mechanism, as I mentioned, can give a rough estimate of the magnetic field, because for radio pulsar we all rely on the P and P dot parameter, and we can easily extract that what should be the rough magnetic field. But as I mentioned, it is not clear previously, but in this letter we try to explain that as the magnetar getting older and older, the dipole magnetic braking approximation is not valid. So you have to take care self-consistently, because the angle becomes smaller and smaller, and also the source goes towards their depth. So these two information should be taken care for older magnetar. But for younger magnetar, again the dipole approximation can give like measurement of magnetic field as it's happening. You can see the magnetic field does not vary much for the sources which are far above their depth line. But the sources, if goes below their depth, then this problem arises. So you can see below their depth line, the magnetic field, where what we measure from dipole approximation, it is very low in this zone. But since the source already come down in this zone, so magnetic field you can see very high, almost 1 order larger.
Okay, thank you.
Yeah.
Are there other questions? So for your chi log, is it a real geometrical angle or is it a?
Chi naught is that oblique angle between magnetic and rotation axis.
I see.
Yeah.
And why is it changing over time?
No, this is because the torque will operate, as I mentioned in that this one. So this is evolution equation of that oblique angle chi. So as that angular momentum extraction happening because of three torque, like gravitational wave torque, particle wind, and also dipole radiation. So this torque will also change this oblique angle. So that's why it's changing with time.
Okay, I see. Thank you.
Yeah. Thank you very much. Should I stop sharing?
So if there's no more question, then let's thank our speakers again.
Okay. Thank you very much. So stop sharing.
So our third talk will be given by Hao again. So Hao, are you ready now?
Yeah, I'm ready.
Okay, so you now have about 22 minutes.
Okay. Yeah, I'll try to finish in 20 minutes or so. Yeah, hopefully the internet works better this time. All right. Yeah, for those who didn't hear the first part of my talk, so I was talking about the TV halos, or in general the pulsar halos around the Minga and monojam pulsar. Okay, so I just skipped those slides I already talked about and continue the rest of my talk. So here's the list of the so-called middle-aged pulsars. So we think these middle-aged pulsars can be the candidates for to contribute for the local pulsar exercise, because they are, on one hand, they are old enough that the pulsatrons can have enough time to travel to the Earth. But on the other hand, they are still young and energetic enough, so they're enough. The pulsatron can be accelerated. So there are actually a strong list of candidates that meet this criteria. And if you look at the first and second, which are the Geminga and the monogam pulsar, and they are actually located in the northern sky, and the good position can be seen by the Hawk Observatory. So Hawk, stands for High Altitude Water Shunkle. It's a gamma observatory located in Mexico, and at the altitude of 4,100 meters. So it utilized this water shunkle detectors with 300 what's called water tanks, and covering this very large detected area, and it's sensitive to from sub-TeV to more than 100 TeV gamma rays. So the key thing here is it has very wide field of view. Actually monitor the overhead sky for all the time, and the field of view is about 2 steradian at any time, and also high duty cycle. It runs 24/7. And so the full detector start operational in 2015. Okay, so going to some results. So before showing Hawk result, here is the Milagro 8 years data. And you can see Geminga with a point source search map. It shows some 3 sigma hotspot, and if you smooth it to additional 1 degree, it's like 6.6 sigma, which means this is an extended source. And with only 1 year, little more than 1 year of Hawk data, we see Geminga much more clearly, also as well as the monogam, so-called the pulsar BO656 plus 14. They are actually located, fairly close in the sky, and only a few degrees apart, and the distance also 200 some parsecs from the Earth. So you can see this very extended gamma emission, and much larger than a typical possible nebula like observed in X-rays. So with high statistics, we can now plot the radial profile of these 2 sources. Left is Geminga and the right is monogam. So you can see the data, which in black is well matched the so-called diffusion model, which is in red. So I think the scenario here is these electron and positrons accelerated from the central pulsar nebula, and diffuse into a much larger region, which is tens of parsecs, and make gamma rays through inverse Compton scattering. So from this result, we can actually measure the diffusion coefficient based on this profile. And what we found is the diffusion coefficient we measure here is about 2 orders of magnitude lower than the average diffusion coefficient in our galaxy, which is derived from the boron to carbon ratio measurement. So in this plot, you can see, the circle here is indicates what the Hawk measurement, and if you, our measurement is at 100 TeV electrons, and if we extrapolate using the common like 1/3 diffusion index, and it's like the dashed line, and comparing to other boron to carbon ratio lines, you can see it's much lower. So this is the kind of a surprising result, but on the other hand, maybe not that surprising, because the boron to carbon ratio is the diffusion coefficient averaged in our galaxy, and in fact, the cosmic rays spend much more time in the halo of galaxy, where the diffusion is expected to be faster. But if you're talking about like a certain region in our galaxy, we really don't have much idea how fast or how slow it should be. Okay, so if you take this number, take this diffusion coefficient we measured, and then calculate, then ask the question, if we assume this is the same diffusion coefficient all the way to the Earth, and how much positrons can propagate to the Earth and contribute to the local mirror cosmic ray positron spectrum? The answer is presented in the red plot, where the green dots are the AMS measurement, and the blue curve is from the contribution from Geminga, and the shaded area is the statistic error. So you can see the contribution is actually much lower than the what we expect from AMS. So we kind of, I mean, under some assumption, we rule out the scenario that the Pulsar exercise is majorly contributed from this pulsar. So I mean, that has been a while since our paper published, and there are many follow-up papers. Actually, I mean, some on like the nature of this slow diffusion region, but there's many follow-up papers that actually draw the opposite conclusion, that the Hawk results support the nearby pulsar at the origin of the Pulsar exercise. So I will explain here. Well, these are not really contradictory, but they just under some different model assumptions. So I call this one zone versus two zone model. So the one zone model is like what we present here. So the low diffusion coefficient all the way between Geminga to the Earth. So we are kind of living in a low diffusion bubble in the nearby 100 parsecs, and that was our conclusion before. But on the other hand, if you build like a two-zone model, say the diffusion coefficient return to much higher value beyond around 30 parsecs from Geminga, and then they can contribute about the right amount of electron to positron to the Earth. So in this case, I guess the slow diffusion region is actually generated by the pulsar itself. So talking about the models, I mean, between these two models, I mean, there's definitely like fundamental difference from like on how these low diffusion regions are generated. So the first model, I mean, I guess I just go here. So the first model actually proposing that the low diffusion region is generated by the pulsar itself. So if you just look at the plot to the sketch to the right, so the whole system is within a supernova remnant, and the central region is the so-called pulsar nebula. The typical pulsar nebula we call in X-ray, where the electron positrons are confined by the magnetic field, and between them, actually a larger nebula, so-called TV halo, is what we see here. They are made from escaped electron positron, but I mean, diffusing into a larger region, but still somehow confined by a supernova remnant or some slow diffusion region. So this is the first model, and I think the key thing here is the slow diffusion is limited in a smaller area, probably tens of parsecs, and the nature of it is actually from the pulsar or supernova remnant itself. I mean, under this line, you can follow this line. You can explain some like, for example, the galactic diffuse emission with a combination of many TV halos. I won't go into detail here, but also the positron exercise. If you take many pulsars and build this kind of a two-zone model, to the right, I mean, you can see, I mean, the combination of them might explain the AMS measurements. But on the other hand, a second model, which is more like, say, conservative. So I think the key difference is a TV halo only formed when the pulsar get really old. So like the stage 3 here, the pulsar already escape from the supernova remnant, and the the particles diffuse into the interstellar medium. And in this case, we are actually measuring the diffusion coefficient in the stellar medium. But I mean, there are some common things between the two models. I mean, both predict very large extended emission, gamma emission, and which are both diffusion dominated. And I mean, that might be general feature of the pulsar. The question is at what age do these halos form? And also, like I said, the diffusion coefficient on one hand is moderated by the pulsar, and on the other hand, in the other model is just the general feature of the interstellar medium. Okay, so in the rest, like 10 minutes, I'll say the question about diffusion remains, right? We look at this plot. I mean, the shaded area is approximately the gamma ray observation we have, and we don't know. I mean, in the first model, it's kind of like this, right? I mean, the slow diffusion is limited in this wide region, and then it returns to the faster diffusion to the Earth. And on the other hand, there could be some general feature of the interstellar medium. It's a much larger structure, and it may extend all the way to the Earth. So there are two follow-up studies we would like to do. So first is to see how big the slow diffusion regions. But it is hard to do this, to draw conclusion with Geminga itself, right? Because you can only see gamma ray flux extend to tens of parsecs. And so we have to look for multi halos in order to answer this question. And then the second question, like how does the diffusion depend on energy? And to answer this question, we did some follow-up studies, more detailed observations on Geminga. Okay, so first talk about Geminga with more data. Now we double data set on Geminga, and you can see clearly these two sources, Geminga and Monogen. And more importantly, now since we have more statistics, we can separate the data into a few energy bins. Like in these 4 energy bins, we see at least in the 2 middle bins, we clearly see these 2 sources. And this is just mapped with additional smoothing. You can see clearly these 2 sources. So with these 2 middle energy bins that we have detected Geminga, we can actually draw this radial profile in each bin, the red plots, and calculate the diffusion coefficient as a function of energy. As I show here, the black point is the diffusion coefficient we published earlier, and the blue points are the new measurements. But I mean, unfortunately, I mean, the error bar is still too large, so we really cannot draw good conclusion. I mean, have good constraint on the diffusion index, how it changes with time. You can see the dashed line, the delta equals to 0, or delta equals to 1/3. I mean, we cannot distinguish them. But on the other hand, I think the key thing here is to include also measurement from other experiments, like Fermi at low energy. At GeV energy, Fermi had this measurement in this, as shown in this red dot. And we are, I mean, marginally distinguish these 2 models, but we have to accumulate more data. So I think more data and multi-wavelength study are the key to considering this diffusion index. And on the other hand, if we talk about spectrum, it's also interesting. It shows the multi-wavelength spectrum from GeV to TeV. I mean, it shows this interesting or strange double-humped distribution. So I mean, there are possible explanations to be investigated on the theory side. So I won't go into more details, but I just list a few possible explanations here. Okay, so anyway, and that was the ongoing studies, and also actually there are two more things we should look into. So first is an isotropic diffusion, right? So if you assume, so our previous model assume like isotropic diffusion along every directions, but if we assume that like the diffusion is faster along the magnetic field lines and slower perpendicular to it, I mean, which is naturally a natural assumption, then you assume you will get a like asymmetric or elongated source shape. So we are currently collaborating with Dr. Liu and on this assumption. And also, there's some spatial template fit we are exploring, because currently we don't take into account the like the proper motion or other like asymmetric diffusion and such things. So we are now working with Dr. DeMaro to have this first principle template, and we can apply to the data. And the advantage is not only taking into account promotion and such, but we can directly fit the physical parameters. So instead of fitting, like say, a gamma ray spectrum, we are directly fitting this electron spectrum that are accelerated from the pulsar. So this is just some ongoing analysis. Okay, so in the next 5 minutes or so, it's all about the search for multiple halos. Like I said, it's with Gaminga itself, it's impossible to distinguish these two scenarios. But the advantage of Hawk is we are observing all sky. I mean, at least the northern sky, northern part of the sky. So there are a lot of candidates. So this is actually a new discovery space for Hawk. This plot shows the speed and energy as a function of distance of the known pulsars from the ATNF pulsar catalog. And so with 10 years of Hawk sensitivity, we expect actually like more than a dozen of these TV halos, but of course, depending on how you the definition is. And so, in fact, we already seen some of the halos. After we published the Gaminga paper, there are two more halos found in our galaxy. Interestingly, they are all in the general in near the Gaminga region. Part of the reasons is this region is not as crowded as compared to the inner galaxy, so it's easier to find. It's very extended gamma ray structures, and so both are both the 05443 or the 0635, both are like middle-aged pulsar. They are similar to Gaminga. And also we are extending our search to a bigger population from the ATNF catalog, and we actually found 13 pulsar halo candidates, including some of them not previously known to be TV emitters. Okay, so I'll skip the catalog part, but in our latest catalog, there are two more candidates that are potentially TV halos, and also the pulsar characteristic are similar to Gaminga, which is very interesting. So I mean, I have to add a LASSO page here, because not only Hawk, LASSO is a new located in China. It's still under construction, and the sensitivity is actually effective area is about order of magnitude larger than that of Hawk, so which have a much better sensitivity. And although it is still under construction, but already takes some data with partial array, and probably heard about our publication like 2 months ago about the dozen of PEV emitters. And also published today, there's a new Crab paper, a paper on Crab Nebula, which show the Crab spectrum extend to 1 PeV. It's very interesting result. But anyway, so LASSO already have a few candidates on pulsar halos, and actually one paper has been published on this new pulsar halo 0622. You can see the radar profile in the middle plot, which show the data is also well matched the diffusion model, and to the right you can see how the ICD distributed. Okay, anyway, so let me just conclude my talk. So what we can learn from TV halos. First, the connection to the Pulsar exercise is very interesting. And the second thing, the fine misaligned pulsars, I didn't talk much about it because we all know maybe only one third, or even less than 1/3 of pulsar, which have their like radio beam pulsar emission pointing to the Earth. But other pulsars just invisible or called misaligned to us. But on the other hand, the halo pulsar halo emission is isotropic, so we expect to have much more these deep halos that don't have associated pulsars. So this is a way to find new pulsars. And also the probing interstellar medium characteristics is important. Like I said, we can use pulsars to probe the propagation of cosmic rays in many different regions in our galaxy. And of course, we can have better understand the galactic diffuse emission of the populations through the TV halo observation. So the final word is that more TV halos are anticipated with future data from Hawk and LASSO, and well as from CTA and SWGO, which is proposed experiment in the southern hemisphere, which we haven't covered with Hawk and LASSO. Okay, I will stop here and take questions, and sorry again for the technical issue. Thanks.
Okay, thank you, Hao, for this talk. So we have some time for 1 or 2 questions, maybe. So I seem to recall that you mentioned that with Gaminga and monogam halo only, we cannot distinguish between the 1-zone and 2-zone models. So how more halo discovery can help us on this?
Yeah, so yeah, the problem with the two models, I mean, they limit within the tens of parsecs from the region. I mean, we only see gamma rays within that region, so it's hard to tell what's happening beyond that. But with more pulsar halos, one thing we can do is to see whether if all the diffusion coefficient is low, right? I mean, if all the diffusion coefficient is low, I think we are then more it's more likely the model 1, right? The diffusion, the slow diffusion region is generated by the pulsar itself. So every pulsar have that feature. So it's more like a 2-zone model, right? Since it's generated by the pulsar, and then beyond the tens of parsecs, it returns to the faster diffusion. But if we found some of the sources have slow diffusion, some are faster, which means we are measuring the diffusion coefficient in the interstellar medium. It's just some general features in the interstellar medium, and then I think I will more toward the 1-zone model, which means the slow diffusion is not generated by the pulsar, but just some general characteristic of the interstellar medium. So yeah, that's why I say more TV halos can help. Hope that makes some sense.
So in principle, if the model one is correct, we would expect more halo to be detected, right?
Yeah, I mean, so talking about more halos is depending on the definition, but I would say model one is more correct if we found the more slow diffusion region, and the model two is correct if we found the halos with different faster and slower different region, different coefficients.
And I suppose the sensitivity of the detector is still a key because we have to go.
Yeah, it is. Yeah, the problem is we want to avoid the observation, the sensitivity bias, right? Because I mean, if the diffusion is faster, which means for the same source, the emission will be distributed to a larger region, which is definitely harder for our analysis or for our detection. So yeah, so the sensitivity is key to find a more complete population.
And maybe you have talked about a little bit about this, but can you elaborate on how we distinguish between the two models? I mean, this Suda model and Chorchinti model by observing more.
Yeah, by observation, I think, like I said, it's hard to distinguish them between them using only Gaminga and Monogem. I think it's just key just to I mean, on one hand, we can do some multi-wavelength study looking at possible halos in other wavelengths to see, for example, how the diffusion change with energy and such. But on the other hand, I think the larger population multi-halo detection helps the most. Like I said, if you see, if you believe more in the pseudo model, all pulsars should have this slow diffusion region. But if you think about the model two, then we are just measuring the diffusion in the interstellar medium. So some should be faster and some should be slower.
Yes.
I think that kind of distinguish between them.
Okay, thank you. So are
Thank you.
there other questions? I haven't seen any. By the way, you can also type your questions if you feel like to. So according to schedule, we'll have now 5 minutes coffee break. So we'll come back in 5 minutes. Thank you. Okay. So I think it's time for us to start again. And the next talk will be given by Vitaly, who will be talking about. Hi.
I'm
Yes,
here.
Yes. So maybe you can just start. Yeah.
Yeah.
So please.
Okay.
Yes.
Okay. Okay. Hello, everyone. My name is Vitaly Kim. I am from Fesenkov Astrophysical Institute from Kazakhstan. And today I'll talk about the unique pulsar 1E 16 13 48 -50 55. For short pronunciation, I will pronounce only 1E. It will mean full name of this. 1E is an isolated X-ray pulsar, which is situated in the gaseous nebula RCW103. The estimated distance to RCW is about 3.2 kiloparsec. Its diameter about 7.7 parsec. Its age is estimated as about 2,000 years. 1E has a two-component spectrum, blackbody and power law. An X-ray luminosity of 1E is about 10 in 34 degree arc per second. With effective temperature of blackbody component in the range between 0.6 0.8 kilo electron volt. But the most amazing fact is spin period, which is equal to 24,000 seconds. It's about 6.7 hours. This is a unique pulsar with the longest known period. 1E was discovered in 1979 by Einstein X-ray Cosmic Telescope as a point X-ray source in the gaseous nebula RCW103. Therefore, it has name 1E. This is equatorial coordinates. After the discovery, there appeared the question about its nature. In 90s years of last century, cosmic telescope ASCA found that the source 1E had some variability in luminosity. It was supposed that 1E is a neutron star, and its radiation went from hot spots with a radius about 600 meters. It looked like an accreting pulsar. But the most amazing was a discovery its spin period by means of telescope XMM Newton in 2004. The period was equal to 24 seconds. It's about 6.7 hours. I told about it. Further observation showed that 1E had a spin down with a rate about 10⁻⁹ seconds per second. After the discovery spin period, there appeared some questions about its nature. The first question was about its evolutionary stage. Next question, how this pulsar can reach to such long period during short time, about 2,000 years. This is the age of supernova remnant RCW. Let's try to answer the first question. The pulsar cannot be in the stage of ejector or propeller, because if we compare critical period for the stages of ejector or propeller with its spin period, we can estimate magnetic field of neutron star. These stages take place if the surface magnetic field of neutron star is about more than 10 in 17 degree Gauss. It's doubtful because in 5 times exceeds canonical value for pulsars. It seems like that 1E is an accretor with a radius of magnetosphere estimated from hotspots. Okay, if this pulsar is an accretor, then there is a questions about scenario of accretion realizing on this pulsar. To answer this question, we should compare 3 important characteristic radii. First one, Alvin radius, where dynamical pressure of moving plasma reaches the pressure of magnetic field of neutron star. Second one is the circularization radius. On this, on this radius, angular velocity reaches Keplerian. On this radius, azimuth pressure reaches dynamical in accretion flow. Here you can see a radius of circularization. All parameters you can see here. Okay. If a magnetic field takes place in accreting matter, then in the process of motion toward a neutron star, transverse scale decreases, but longitude scale increases. And due to the law of conservation of magnetic flux, with approaching to a neutron star, the strength of all magnetic field of accretion flow becomes stronger. On the magnetic levitation radius, pressure of magnetic field in accretion flow becomes comparable with dynamic pressure. You can see here. So we have three characteristic radii, and realizing accretion scenario depends on relations between each other. If there is no own magnetic field of accretion flow and Alvin radius is bigger than circularization radius, then quasi-spherical accretion realizes. If the circularization radius exceeds Alvin radius, then accretion realizes with Keplerian disk. If the accretion flow has own magnetic field, we should consider its influence. And if radius of magnetic levitation exceeds Alvin radius, you can see here this is expression. And if radius of magnetic levitation exceeds Alvin radius and circularization radius, we will have a magnetic levitation approximation. Further motion of accreting matter will be controlled by magnetic field of flow. It will lead to formation of non-Keplerian magnetic levitation disk, also known as a magnetically arrested disk or MAD disk. Simple scenario of magnetic levitation accretion was considered in 70s years of the last century in works of Soviet astrophysicist Gennady Besnovatый-Kogan and his colleague Alexander Zumaikin, and continued in the works of Nazar Eksanov from Russia and Mark Finger from the United States. Here you can see common accretion model, which can have three possible approaches. Radius of magnetosphere for classical scenarios is approximately equal to Alvin radius. You can see here. In case of magnetic levitation scenario, radius of magnetosphere is approximately equal to the inner radius of magnetic levitational disk. You can see here parameters. Okay, let's consider one in the frame of common accretion model. In case of quasi-spherical accretion, its age too much exceeds the age of supernova remnant RCW103. If we consider accretion from Keplerian disk, we found that its equilibrium spin period takes place if its magnetic field more than 10 in 15-degree Gauss. The best correspondence with observable data achieves if we consider in the frame of magnetic levitation scenario. In this case, magnetic field of the surface neutron star remains canonical. Its age about 2000 years. Next step is to answer about its origin of the pulsar 1E. We offer two possible ways to explain its origin. In the first way, progenitor of 1E was a normal massive star in a binary system. But in the end of its evolution, a normal star explodes as a supernova, which happened 2000 years ago. After explosion, the binary system disintegrated, and there appeared a neutron star and supernova remnant RCW. In this case, the pulsar 1E must be either an ejector, but it cannot be an ejector, I talked about it, or it could be born as an accretor right away. In this case, the initial spin period must be more than 4 seconds. But in the contemporary understanding of neutron star evolution, it's known that initial spin period, the period of born neutron star less than 1 second. This way is unluckily. We also offer another way of evolution. In the second approach is a Warsaw binary system. And several million years ago, one companion exposed a supernova. and 1E was born after first explosion several million years ago. But the binary system did not disintegrate it, and binary system continued its life and system as a system with a neutron star and normal star. Neutron star within 1E during million years went through all stages of evolution from ejector to accretor. And about 2000 years ago, there was an explosion of massive companion. And the system after that explosion disintegrated. After burst of massive companion, there was born RCW 103 supernova remnant. In this case, 1E is an old neutron star into a young supernova remnant. What conclusions can we do? Observable characteristic of the unique pulsar 1E can be described in the frame of magnetic levitation accretion without the hypothesis of super strong magnetic field. In this case, 1E is accreting neutron stars surrounded a residual magnetic levitation disk. Parameters of 1E, mass, radius, magnetic field in this frame correspond to canonical values for neutron star. The origin of 1E can be explained in the frame of canonical evolution scenario of high mass X-ray binary systems. Second supernova explosion leads to decay of a binary system. In this case, 1E, old neutron star, is a result of the first supernova explosion in binary system, surrounding a residual magnetic levitation disk, which can be formed by means of gravitational capture from expanding supernova shell. Thanks for attention. My talk was short. Are there any questions?
Oh, thank you, Vitaly.
Yeah.
Thanks for keeping the time. So it's time for questions. I'm just wondering, what are there any other models for this slow spinning pulsar? You talk about two, right?
It's a known model, but unfortunately, is not popular model of magnetic levitation accretion. This model was developed by Bisnavati Kogan. This is astrophysicist from Institute of Cosmic Research in Moscow, and also his works continued by Nazar Eksanov and Mark Finger. We published some articles about it in Astrophysics and Space Science and Astronomy reports. You can read it, articles you can see in NASA ADS portal. Unfortunately, I couldn't show here all mathematical interpretation because there are a lot of mathematical equations, and it's needed more time to explain full model.
So can you explain the occurrence rate of such a slow pulsar in your model? So do you need fine-tuning? Have you estimated the occurrence rate? So we've seen such a slow pulsar, and it's very
occurrence rate. Unfortunately, we didn't estimate it because this is a unique case. Only one pulsar is known in our universe.
Yes.
You mean possibility of the birth, estimation of possibility of the birth? Yes.
I mean, can you? Yeah. Is it consistent that we expect only one in, say, 5,000 pulsar that that will have such a large spin period.
We also suppose that AXP SGR can also be described in our model of magnetic levitation accretion. It's about what? It's about 50 pulsars or 40 pulsars, AXP and SGR. We also can explain it in the model of magnetic levitation scenario. But they are not sufficient long periodic, but their period is sufficient that there is problem with classical accretion scenario. But we can explain AXP and SGR with canonical values of neutron stars without a hypothesis of magnetars existence.
A related question would be, so what is the most special characteristics of this so-called binaries, such that such a slow pulsar form? I mean, do we need fine-tuning?
What?
I mean, what is the most special characteristic in this system compared to others?
In a system of high mass X-ray binary, you mean here picture, yeah? Or you mean model?
Yes, I mean, if your model is correct, then what makes such a system? What parameters control the spin period?
The model of magnetic levitation accretion makes more effective the process of breaking of neutron star, and therefore the modeling estimation of spin down rate is more effective than is compared with Keplerian disk or quasi-spherical accretion. Because of radius magnetosphere in the model of magnetic levitation accretion is less than Alvin radius. Therefore, the process of breaking of neutron star will be more effective in the frame of magnetic levitation accretion.
Okay, I see. Thank you.
Thanks.
So I don't see any more questions. So let's thank our speaker again. And the next one will be given by Liam Dun, who will be talking about pulsar timing and glitch detection by hidden Markov model.
Yes, thank you. So I hope everyone can see that and hear me.
Yes.
Good. Yes. So thank you for the opportunity to speak today. So I'm going to talk about this work that we've been doing over the past few years, with a group at University of Melbourne, Andrew Milados, Sofia Suvrova, Rob Evans, and Bill Moran, and we've also had a lot of help from Stefan Oslovsky, Marcus Lower, and Matthew Bales at Swinburne. So I'm just going to start with a very quick overview of radio pulsar timing. So if you point your radio telescope at a typical sort of bright radio pulsar where you can see individual pulses, you see something like on the left where time is going up the page here, and so you have a wide variety of different kind of pulse shapes over time. But if you stack all these pulses and average them out over a time period of 5-10 minutes, then you get quite a stable pulse profile like you see in the middle panel, with some evolution over observing frequency, but otherwise it's stable on timescales of years for the most part. And so the basic idea of pulsar timing is that you can construct these standard profiles for each pulsar, and then with subsequent observations you can correlate the standard profile with the observed profile, and basically you get from each observation you get a timestamp which gives you a very accurate determination of the pulsar's rotational phase. So basically each of these times of arrival or TOAs tell you basically when the pulsar's phase is a sort of fiducial fixed value, which normally just take to be 0 by convention. And so the normal way that you use these TOAs is you construct a sort of a phase model, which after you've done the sort of transformation from the site of the radio telescope into the solar system barycenter, it usually just takes the form of a Taylor series in time. And so you Taylor expand and you have a frequency term and a frequency derivative term and maybe some higher terms. And basically you fit the model to the TOAs that you measure, and you get some timing residuals, which is the difference between the measured times of arrival and the arrival times that are predicted by a phase model. And you see a sort of typical example of a fairly normal pulsar on the right, sorry. And basically all of the sort of, any sort of irregularities in your pulsar, then in terms of timing irregularities, are recognized as some sort of feature in these timing residuals. Okay, so that's the kind of standard picture. And we are hoping to sort of do something a little bit different, which is based on this idea of a hidden Markov model. So I'll just give a quick sort of cartoon overview of what that is. So in this sort of framework, we have a system of interest, which has a hidden state, which is not observed directly. And we assume that hidden state of the system is evolving over time. And very importantly, we assume that the evolution is Markovian, so it has no memory. And then we sort of say that whatever observations of the system that we do make are connected to the hidden state probabilistically. So we sort of have this probability function which tells you the probability of making any given observation of the system conditioned on the hidden state of the system. So in the context of pulsar timing, we make the choice to have the combination of the frequency and frequency derivative as the hidden state of the system of the pulsar. And we're going to model the evolution of that hidden state as a sort of a Markovian noise process. And just as in traditional pulsar timing, the times of arrival are the data, and we start from the barycenter TOA, so all of the sort of transformation from the site TOAs is done with existing software like Tempo2, and we're making exactly the same essential assumption as usual, that the TOAs correspond to timestamps of constant rotational phase. And we're going to say that the probability of observing a given gap between two consecutive TOAs for a given combination of F and F dot is expressed as a von Mises distribution. So this is basically the Gaussian on a circle. And so just to give a little bit of sort of pictorial representation to these two things. So for the transitions between hidden states, in this work, we're always going to assume that the evolution is driven by a random walk in the torque. This is not a sort of essential assumption. You could have a random walk in the frequency or in some sort of lower derivative, or a completely different prescription, just as long as it's Markovian. And so the figure on the right there is just showing what this kind of looks like schematically. So we have frequency on the x-axis and frequency derivative on the y-axis. And we imagine that we start at the yellow dot over on the right, and we let the system evolve for some like a few days kind of. And after letting the system evolve, you have this probability distribution for where the system can end up. And so it's centered on the unfilled diamond. That's kind of the evolution that you get in the presence of no noise, but noise sort of spreads it out and you get this sort of skew normal distribution. And as for observations, so it's a bit tricky because in general, a lot of different F and F dot pairs are going to be consistent with a given TOA gap. So if you sort of have a TOA gap of 10 to the 6 seconds, then you could imagine having an F and F dot pair that gives you 1 million pulses in that TOA gap. But you could just as well have a different F and F dot pair, which gives you 1 million plus 1 pulses, and both of those will be consistent with that TOA gap. And so you get this kind of multiply peaked distribution when you look at it in sort of frequency and frequency derivative space. And so the idea is to take this model and apply it to the data and see basically what we can compute from this. And it turns out that there are efficient algorithms that are sort of based in the HMM framework to compute several useful quantities. So one of them is the model evidence, the probability of the data given the model. And so this is computed with something using something called the forward algorithm. Another useful thing is the posterior distribution on the hidden states at each time step, conditioned on the data and the model. And so this is a sort of computed using an extension of the forward algorithm called the forward-backward algorithm. And these first two are the ones that we're going to use mostly in this work, but also a useful thing that you could think about computing is the sequence of the most likely sequence of hidden states given some data and model. And that's computed using a completely separate algorithm called the Tobii algorithm. Okay, so a sort of quick, sort of easy first thing to try and do, given some data, is to track the frequency of the pulsar. And so this is showing some real data from the Molonglo radio telescope of Vela. And so in the top panel we have this is showing this is a heat map of the log posterior on frequency as a function of time. And in the bottom panel is showing basically the mode of the posterior at each TOA. So this is like the sequence of most likely frequencies. And so you can see, some sort of wobble in the frequency as it goes along. And so this is a sort of classic example of timing noise, which is quite strong in Vela. Okay. So the main motivation for this work was to study glitches. And so glitches, just to recap again, are a sudden increase in the spin frequency of pulsars. Often they're associated with a change in the spin down rate or have some sort of quasi-exponential recovery associated with them. There are about 600 glitches recorded to date across about 200 pulsars. And the physical mechanism is not known. We don't know why glitches happen or sort of what underlying dynamics are at work. And so on the right, this is showing a picture from the paper reporting the very first detection of a glitch. So this is showing period versus time. This was also in the Vela pulsar. And so you can see that on about the 1st of March, there is a huge jump. Well, I say huge. There's a jump of about 196 nanoseconds in the spin period. And this is a fractional change of about 2 in a million, I believe, 2 parts in a million. So these are sort of small fractional changes, but pulsars are sufficiently accurate timers that you can notice changes like this quite easily. But it's not always so easy. So recognizing glitches is not always straightforward. So the typical way that you do it is you have some timing residuals from your pulsar, and you're looking for features in those residuals that you can associate with a glitch. And so this figure on the right is showing some residuals from an observation of J1833 minus 1034 over several years. And the arrows there indicate where glitches have been reported. And so it's sort of not clear at this point, I think, whether all of those glitch locations correspond to a sort of true glitch in the data, or just some sort of small excursion in timing noise. And it's even harder because you have this sort of in some cases, quite long observing cadence. And so we would like to sort of have a way of detecting glitches, which whether or not we sort of are able to detect all glitches or most glitches, we would like to have a way that gives us a better feeling for when we can be confident in a glitch detection. Some sort of quantitative measure that we can put on a detection. And so in the HMM framework, I mentioned that the probability of the data given the model is sort of easy and efficient to compute. And so the idea with this is that we're going to phrase the question of, is there a glitch during the kth TOA gap, for whatever k might be, as a question about Bayes factors. So we're going to construct, for the kth TOA gap, we're going to construct the Bayes factor, which is the probability of the data given the model where there's a glitch during that kth TOA gap, divided by the probability of the data where there's given the model with no glitch. And we're going to set some sort of Bayes factor threshold above which we will sort of say that we have a glitch candidate, and below which we will not. And just to sort of say that the size of the glitch is not a part of the model. The glitch size will be inferred later on when you come to do frequency tracking. So to give a sort of clear, easy example of how this goes, this is again some data from Vela, this time taken at Parkes, of a glitch that happened back in 2016. And so on the top panel, we have the timing residuals. And so you can see that at about 300 days, the timing residuals go haywire because there's been quite a large glitch. And in the bottom panel, we're showing the log of the base factor for a glitch at each time step from the HMM. And so the log of this base factor has a clear peak at almost exactly the same time, with a log base factor of above 1,000 in this case, which is more than decisive. So that's kind of just a simple example of how this goes. And frequency tracking through glitches sort of goes as you'd expect. This is a glitch in J1731 observed at Molonglo. And so there's been a glitch at about the 103rd TOA in this data set. And you can see from the frequency from the posterior that the size of the glitch is about 4 × 10⁻⁶ hertz. And so that's quite a straightforward example. But this is, I just want to spend a little bit of time talking about this example, which is a little bit less straightforward. So this is another glitch at Molonglo. This is in J1709 -4429. And so you can see that there was a glitch reported in this pulsar at about the 83rd TOA. And you can sort of see that, but you'll notice that the posterior after the glitch is multiply peaked. There are 3 peaks, which is kind of strange. It's telling you that the data from Molonglo are consistent with these 3 widely separated glitch sizes. And so we spent a bit of time investigating this, and it turns out that basically, because Molonglo observes pulsars on a very regular schedule, because it's a transit telescope, you can kind of get this aliasing effect where timing models with frequencies that are widely separated by about 10⁻⁵ hertz are all consistent with the data. And so this glitch was initially reported as having a glitch size of about 5 × 10⁻⁷ hertz. But when we combined this Molonglo data with data from Parkes, which doesn't have the same sort of observing schedule, you find that the glitch size is actually more like 2.4 × 10⁻⁵ hertz. So the initial glitch size was in error by a factor of about 40 in that case. And so the point of showing this is basically that it's very hard when you're just looking at the timing residuals to notice this kind of thing. But if you have something like this frequency posterior, then you can immediately see that there's something else going on with these multiple peaks. Okay, and so the sort of basic prescription for searching for glitches with this technique is you first decide on a base factor threshold. You decide on that based on sort of basically what false alarm rate you're willing to tolerate. Normally we set it to be a roughly 1% false alarm rate, which ends up being a log base factor. A base factor threshold of about √10. And so then once you've done that, you go and compute all your base factors for all your TOA gaps in the data, and you look to see do any of them exceed this threshold. And if they do, you have a glitch candidate. You can perform follow-up analysis, do frequency tracking to find the glitch size and all that sort of thing. And then finally, what you can do is you can compute upper limits on the size of undetected glitches. And so the idea here is basically you have some given set of TOAs from a pulsar and you don't detect any glitches. And you want to know what you can say about undetected glitches in the data. Basically, the most interesting thing is how big can they be? And so the way that we approach this problem is to estimate the detection rate, P sub d, for a variety of glitch sizes. And we do this by making a whole lot of synthetic data injections with we're sort of averaging over the epoch of the glitch. But we make about 100 realizations per delta F value. And we run the HMM on all of those and we estimate the detection rate from that. And so you get some sort of sigmoid curve, like you see on the right there, with the log of delta F on the x-axis and the detection rate on the y-axis. And basically you choose some sort of alpha% upper limit, which is the delta F value for which the probability of detection is alpha%. And in this case, we're going to choose 90%. So we have done this for pulsars in the first UTMOST data release. So UTMOST is the timing program that's run at the Molonglo telescope. So most of these data sets cover about a 3-year time span. So we searched all isolated pulsars for glitches, which is 283 of them. and we found only glitches that had been previously reported. But then we went and we set upper limits on the size of undetected glitches for every pulsar that we searched, except for one, which I'll say a little bit about. But what that looks like is what you see on the right there. So in the orange is the histogram of the upper limits, and in the blue is just the distribution of glitch sizes from the George Bank catalog across the whole population. So we're excluding a pretty sizable chunk of the glitch population, but there's clearly some small glitches which we're not sensitive to and which we can't exclude in the dataset. And the one pulsar that we weren't able to set upper limits for, but we searched, was the Magnetar J1622, which was just, we weren't able to set upper limits because basically the timing noise is too great in the pulsar for us to deal with at this stage. Okay, so finally, I want to talk about a related sort of application, but thinking not about searching archival data, but searching data as it's acquired. So because we have this sort of automated glitch detection pipeline, it's practical to time many pulsars at a high cadence and search them for glitches basically online. And because the HMM is computationally quite cheap, we can pretty easily do this for roughly a couple of hundred pulsars with a daily or nearly daily observing cadence. And so this is an opportunity for high cadence timing programs like Utmost to detect glitches quite soon after they occur, and to sort of send out alerts for other facilities to follow up, which might be other sort of radio facilities or other optical or X-ray telescopes or whatever. But also gravitational wave searches would generally, because glitches are a target for some searches, it's advantageous for those groups to have sort of timely updates of glitch detections, rather than, in some cases, waiting years before they're reported. So just to give a little idea of what kind of capability we have for this. So this is showing a simulated sort of observing campaign of this pulsar J1740, which is quite a frequent glitcher, with a nearly daily observing cadence. So we sort of simulated daily cadence and then dropped a quarter of the TOAs to sort of simulate lost TOAs due to RFI and that sort of thing. And so there are two glitches injected into this data set at about the 53rd and 170th TOA or so. And we're imagining that we're searching in this sort of 50 TOA window. So we start with the first 50, and then each time we get a new TOA, we drop off the oldest TOA and sort of move along like that. And so the blue bands are basically showing where you would expect to possibly make a detection of the glitch, basically whenever your window overlaps with the actual glitch that's been injected. And on the y-axis, you have the log base factor, the maximum log base factor across that window. And so you can see that for both the 5 nanohertz and 10 nanohertz glitches, in this case, we detect both quite confidently within a few days, basically, of the glitch occurring. And so we would be able to make a confident detection and sort of encourage follow-up, basically, if we saw something like that. Okay, so to sum up, pulsar timing with hidden Markov models is sort of offering this complementary approach to more traditional techniques. We explicitly track the evolution of frequency and frequency derivative, but still using time of arrival measurements. We apply it to glitch detection. We can construct a sort of automated, quantitative, and computationally cheap detector. And we can evaluate the performance of this detector through synthetic data injections and set upper limits on the size of undetected glitches. And as I said at the end, we can also think about doing this kind of low latency detection as well. That's it. Thank you.
Okay, thank you, Liam, for keeping the time. So we have time for a few questions. So I have two questions concerning. So have you reproduced all the glitches that have been reported before using this?
No. Yeah. Yeah. So we research Utmost. No. So we find all the ones that are basically above the upper limits that we set, but there are a couple that were reported that were very small. which we wouldn't have expected to detect, but so we can't sort of exclude them.
Okay, so still combining our eyes and computer would give us a more complete catalog, right?
Right. Yes, you would. But you have to also be thinking about questions of whether those small glitches are really glitches or just sort of timing noise excursions that have been picked up by eye. But can't be sort of you can't make a quantitative analysis assessment of how confident you can be necessarily in those small glitches.
The limit is something like 10 nanosecond.
What limit do you mean? Sorry.
So in your approach, the limit to the glitch is something like 10 nanosecond, right?
Yes. Yes, the sensitivity. Yes, the limiting sensitivity is something like that. Yes, it depends. Of course, it varies depending on the pulsar and all that. But yes, roughly, that's right.
Have you discovered any glitch from millisecond pulsars?
No, we haven't. I mean, that would be very exciting, of course. And there was this recent event in J1713 which we had a look at, but no, basically, not yet.
Okay. Are there any other questions? So, if no, thanks, I'll skip again, and let's move on to the last talk, who will be given by Mac, who'll be talking about an updated glitch rate age law inferred from radio pulsars.
Okay, great, thank you. Let me share my screen.
Till the end of this section, right?
Yeah, last one.
First one to come.
Okay, and you can just check in again. You can see it looks good.
Yes.
Okay, great. So thank you for giving me the opportunity to talk and for sticking around. I know it's the end of a long conference and there's lots of interesting parallel sessions. But yeah, so my name is Meg. I'm from the University of Melbourne and I'm part of AusGrav, which is the sort of Australia-wide Center for Gravitational Wave Discovery. And today I'm going to be talking about an inferred glitch rate age law from some radio pulsars. Okay, so a brief outline. First, I'll give a little bit of an overview of pulsar glitches, why they're of interest and sort of the status of the current glitch population. Then I'll introduce a particular glitch rate age model we want to look at and infer the parameters of. And then I'll discuss the data sets we've used in this work. And specifically what's sort of different about this work is we're looking at including pulsars with no observed glitches so far. So looking at how widening our data set can impact our inferences. And then I'll show the results of the parameter estimation for this particular model we're looking at. And then I'll briefly talk about some of the glitch catalog completeness. Okay, I probably don't need to give another overview of pulsar glitches, but I have a little intro slide anyways. So we know from electromagnetic observations that pulsars generally are seen to spin down secularly, but occasionally we see rapid spin-up events, or what are known as pulsar glitches. These glitches happen over very short timescales, at least relative to the lifetime of the pulsar, and the magnitude of the glitches are pretty small, you know, something like 1 part in 10 to the 5 or less. But as Liam mentioned earlier, the timing precision is good enough that they are detectable. As far as what causes these rapid spin-up events, obviously the exact mechanism is still unknown and is an active area of research. So one possibility is that the trigger mechanism involves some interaction between the rigid outer crust and then the superfluid core of that star. It could be caused by something like vortex impinging in that superfluid. And so basically, because that superfluid core is frictionless, we don't expect it to spin down at the same rate as the outer crust, which is slowing due to probably electromagnetic braking. So therefore, the core will generally be spinning faster than the crust. So an exchange of angular momentum between the crust and core will result in these little spin-up events. And why these are interesting is that as of right now, basically all of our observations of neutron star behavior comes from information we get from the outer crust or outside the neutron star. So that's what gives off your radio or X-ray emission. Maybe in the future, we can use gravitational waves. If we detect gravitational waves from isolated rotating neutron stars, that could teach us about what's in the core, where the bulk of the matter is. But for now, we're sort of limited by what we can observe. This means glitches, which are perhaps an interaction between the outer crust and the inner core, could give us a unique opportunity to understand sort of what's going on in that ultra dense region. And could lead to some new insights into neutron star interiors. So for example, if you could use the glitch sizes to put limits on them, you could use glitch sizes to put limits on the moments of inertia, and that could help narrow down the equation of state a bit. Okay, so a little bit of an overview of pulsar glitches, how they're detected and what has been detected so far. So typically, pulsar glitches are found via discrepancies in the times of arrival. So when they don't line up with that sort of predicted secular spin down. And so far, about 200 different objects have been observed to have glitched, with over 500 glitches observed to date. I believe Liam said 600, so that's over 500, close enough. And the pulsar glitching behavior doesn't seem to be the same across the whole population of observed neutron stars. So of all those glitches, most pulsars have only glitched a couple times, so once or twice, maybe 3 times, and then a small number have glitched, over 10 times. And then also of note is that only 2 millisecond pulsars have been observed to glitch, maybe plus or minus 1 millisecond pulsar, but regardless, it's a very, very small number of millisecond pulsars. So it could be that they're part of a different population that don't have the same trigger mechanisms as the younger non-millisecond pulsars. And I note that just beyond the actual number of glitches, the glitching behavior itself seems to differ somewhat. So for example, a few pulsars are consistent with glitching quasi-periodically. For example, Vela glitches about once every 3 years. Others seem to glitch according to a homogeneous Poisson process. And there's some recent work that shows that maybe some, like the crab, can be described by an inhomogeneous Poisson process, so that the glitch rate appears to change about every 10 years. And then, of course, there are still some pulsars where there have not been enough glitches detected to say anything about, their glitching behavior in terms of quasi-periodic or not. So one of the natural questions is, given that we see a range of glitching behavior among pulsars, can we link that to some other observable properties of the objects? So for example, the characteristic spin down age, the period, the spin down rate, torque, something like that. So you can think of it on your typical PP diagram. If you're to plot the number of glitches on top of that, would you see any trend? And then could you get any additional information out of that? And previous work has indeed shown evidence for an inverse relation between the rate at which a pulsar glitches and its characteristic spin down age. So younger pulsars seem to glitch more often. And like I said earlier, understanding pulsar glitch properties at a global level too can help us learn about what's going on in the interior of these neutron stars. So something like this rate-age relationship may indicate something like how the abundance and depth of pinning potentials within the superfluid evolve as the star ages. And if that relation between the pulsar characteristic spin down age holds, that means we can get valuable information from pulsars that have only 1 recorded glitch, or even pulsars that to date have no recorded glitches, or at least haven't glitched in the time that we've been observing them. Understandably, a lot of previous work has focused on pulsars that have numerous recorded glitches. But what we want to do in this work is to show that widening your data set can have an effect on your estimated properties of your model of interest. So in this specific work, what we set out to do is estimate the properties of one potential glitch rate age relation. So first we assume that the glitch activity can be described as a homogeneous Poisson process given by normal distribution here. And then for this work, we model that Poisson rate lambda as equal to some constant A over the characteristic spin down age of the pulsar raised to some power gamma, where the characteristic spin down age is defined as usual. And for convenience, we put things in terms of a reference age, which we've set to 1 year. And what we want to do is we want to estimate A and gamma given our pulsar populations. But we're going to do this using 2 different data sets. First, we'll use just the pulsars that have been observed to have glitched at least once. And then to that data set, we'll add a population of pulsars that have no observed glitches thus far. And we'll see how expanding this data set can update our estimates and why it might be important to make sure we're trying to capture as wide a range of pulsar behavior as possible. Some more specific details on which pulsars we've included in this analysis. So we use both the Australia Telescope National Facility Pulsar Catalog, as well as the Jodrell Bank Catalog. And we use pulsars that have 1 recorded glitch over the last 50-ish years or however long they've been observed. So nothing particularly fancy going on in that data selection. And then the only other requirement is that because our model for the glitch rate depends on pulsar characteristic age, we obviously can only use pulsars with an associated age estimate. So in total, that gives us 178 glitching pulsars. And of those 178, most had small glitches. Small glitch numbers. So 101 of them have only glitched once. Now for the data set that includes non-glitching pulsars. This is kind of a trickier data set to construct. There are definitely lots of pulsars that have not yet been observed to have glitched, but also many of those pulsars are not routinely monitored. So they very well could have, excuse me, sorry, my computer popped up or something. So they're, where was I? Yeah, so, a lot of pulsars that have not been, a lot of pulsars are not routinely monitored if they're not known to glitch. So it's very likely that they could have glitched sometime in between the last time they were observed and now. And then also, as I mentioned before, millisecond pulsar glitches are exceedingly rare. Only 2 or so millisecond pulsars have ever been observed to have glitched. And some literature has proposed that these millisecond pulsars, again, are part of a separate population and don't glitch by the same mechanism as non-millisecond pulsars do. So the approach we took here is to select pulsars which have been routinely monitored by UTMOST, so from the Molonglo radio telescope. And specifically, we use a data set that was produced by Liam Dunn, using the methodology conveniently described in the talk right before this. So as a brief recap, Liam et al. Used a hidden Markov model to track pulse frequency and its time derivative, and then performs a Bayesian analysis to perform Bayesian model selection to select between the models that do and do not contain a glitch. So we've used the results of that analysis here, and we've included pulsars which were routinely monitored, but for which 0 glitches were found. And then again, we still have the constraint that we only use pulsars for which we can find an associated age estimate. And for the millisecond pulsar question, even though there is a possibility that their low glitch rate is consistent with our age rate model, we've decided not to include them, at least in this first preliminary work. And in total, we have 233 pulsars with 0 observed glitches to date in this second data set. And just to give you a sense of what kind of pulsars are in these data sets, here I show the distribution of the characteristic spin down age for the data set with pulsars that have and have not been seen to have glitched. So the blue is are pulsars with associated glitches, and the orange are pulsars that have not yet glitched during the observation period. And we see that on average, the pulsars with associated glitches are younger. Again, this sort of further indicates that older objects glitch less frequently. And thus, by including them in our data set, we could get more accurate estimates of our glitch rate age relation. And one more thing I wanted to mention, or one more thing I wanted to point out, is that we did check that pulsars with only one observed glitch wasn't primarily due to some observational selection effect, meaning, maybe they're just pulsars that have not been observed for particularly long. So again, assuming that the glitch rate follows a homogeneous Poisson process, we estimate the glitch rate for each of the pulsars, and we plot the cumulative distribution of our estimate of the glitch rate for pulsars with only one observed glitch in orange here, and then multiple glitches in blue. And we see that, overall, the pulsars with only one associated glitch do have lower glitch rates, and that they are adding some new information out of including these low glitching pulsars. Okay, so now that leads me to results of the estimates of the parameter estimation for our assumed model. So as a reminder, we assume that pulsar glitch rate is equal to some constant over the characteristic age raised to some power of gamma. And here we used the Dynasty Python package, which uses nested sampling to produce posterior probability distributions of those parameters of interest. And we use those two data sets. So those that only include glitching pulsars and those that include the pulsars that we haven't seen glitch yet. So the left is only pulsars that glitch, whereas the right is pulsars that we haven't seen glitch yet. And these are just the posterior distributions of those parameters. And I've included here the median of each parameter with the upper and lower bounds on the 90% credible interval. And you see that, probably unsurprisingly, including the non-glitching pulsars or pulsars that haven't glitched in the observation period, does change your estimates quite a bit. So basically, this means that if you really want to start to pin down a relation between glitch activity and age, or some other parameters, doesn't even need to be the specific model. By not including low glitch rate pulsars, you could be getting incorrect or incomplete estimates. And I would also like to note that both of these data sets exclude gamma less than or equal to 0, at least at the 99% credible interval level. So this just further supports the idea that glitch rate and pulsar age are inversely proportional. It also excludes gamma equals 1 specifically, which I believe there was some earlier literature that suggested it could have been just a direct relationship, something over the age. So maybe that's of interest to some people. But again, it's not particularly surprising that we again recovered this inverse relationship between rate and age, but did it in a different way in this case using Bayesian formalism. Okay, and one thing worth noting, of course, is that the results of almost any sort of population level analysis like this can be affected by the completeness of the glitch catalog. Current glitch catalogs are almost certainly incomplete to some point, just because it can be hard to detect glitches. Again, Liam just shared some reasons why it can be difficult to detect certain types of glitches. And for one thing, there are pulsars that are not routinely monitored, and they could quite possibly have glitched since the last time they were observed. And for pulsars that are more or less routinely monitored, even there are some potential missed glitches. This could be for a couple reasons. For example, it could be multiple smaller glitches being misidentified as one larger glitch. So since telescopes usually aren't so lucky as to catch a pulsar exactly at the time of a glitch, if 2 or more glitches occur between observation periods, it could be difficult to disentangle them. Furthermore, there could be a limit on how small of a glitch can be resolved. This could possibly mean missing some smaller glitches. So there are several ways you could try to assess this completeness of the glitch catalog. Some previous work has looked at, testing via Monte Carlo injections. But what we looked at in this paper was to estimate whether the rate of glitch detection is evolving as we expect it to. And so this was something originally that George Howitt looked at in his thesis. I'm using this paper, so thank you to George for this plot. And overall, we expect the rate at which we discover new glitches to increase over time. This is because new glitching pulsars are regularly or somewhat regularly being discovered. So one would expect increased glitch discovery from both these new pulsars, as well as the pulsars we know, already occasionally glitch and we monitor them. So, we expect that as we observe new pulsars, the number of glitches we detect per year or per some amount of time should increase. So if the rate of glitching pulsar discovery is approximately linear in time, then you can estimate the rate of glitch detection. You can estimate that that should follow approximately a quadratic trend. So in this plot, we show the cumulative number of first glitches detected. That's the orange line, and then the cumulative number of total glitches detected, and that is the blue line. And you can see that the number of first glitches detected is roughly linear, as we sort of guessed, and the total number of glitches detected, cumulative number, starting around 20 years ago or 10 years ago, it starts to sort of lag behind what we would guess from sort of the simple scaling. You can see it does have like a little bit of a noticeable change in trend there. So, this could be due to some other totally reasonable effect, but it's also possible that we're missing quite a few glitches in our catalog. We could be missing up to something like 200 glitches. So in future studies, this is something to be aware of and take into account how this could affect our estimates. Okay, yeah, and that brings me to the conclusions, almost right on time. There's some current work ongoing that I'm doing, current future work, to extend the rate model to something more generic. So rather than the spin down age specifically, sort of the period and P dot or frequency and frequency dot so independently, as well as investigating the impact of the observation time per pulsar for the pulsars with no observed glitches and potentially the pulsars with one glitch. Yeah, and then, in summary, pulsar glitches provide a unique opportunity to understand more about neutron stars and try to figure out what's going on in the neutron star interior. And if we want to understand population level properties of these pulsars, those with no observed glitches or small amounts of observed glitches can be important to include in your data analysis as well. And finally, understanding the completeness of glitch catalogs can be important for future work. So thank you.
Thank you for the nice talk. So we have time for a few questions. Are there any questions?
Everyone's ready to move on after the, no, it's fine.
I always have some stupid questions, but so can you go back a little, one slide?
Mm-hmm.
Yeah, so there is a obvious change of slope at 56,000 maybe. So what time is it? Is it like 10 years ago?
I think it's about 10 years ago. Yeah, so not exactly sure what.
So I'm just wondering, is it because of the, so you mentioned something like several glitches merging together, so we could not detect it. Could it also be because of the, like we humans are observing more, say, millisecond pulsars to look for gravitational wave or change of strategy, or is it due to more technical limits? So is it a limit or is it a technical limit or physical limit?
So I think it's an open question. It's unclear. It could be a mix of both. Like, maybe we're, with better instruments, we're specifically observing more older neutron stars for some reason. I'm not sure exactly why, but yeah, so it's an open question. I would guess it's a mix of both technical and maybe what we're choosing to observe. But yeah, it is interesting though.
Yeah, because it's just it's so sharp. It doesn't seem to be. There must be something happening there, right? Either our strategy changes or there's some threshold of the, you know, that we have hit. I don't know. Would be interesting. Okay. Are there any other questions? So if not, I thank all the speakers in this section, and thank you all for attending. And although we have a few participants here, but I think we have quite a more intimate interaction among our participants. So then let's conclude and wish you a nice day. Thank you.
Thank you.
Bye-bye.
Bye.